Let us begin the simulation of the buck converter. We shall go to the applications, start up the GEDA schematic. So this is our schematic capture unit. Let me go here and first save this. I will put it into DC and let me call this as I have cleaned up the DC folder, and we will call this one as buck. So we have the .sh file here. So now we will start loading in the components, and like before, I will go into the components. We need capacitance, we need a voltage source, not sine wave, this is the default, we will change that one to DC voltage source. We will need a diode, we will need an inductor, we will need a resistor for the load, then we will need a power switch, control switch. So this is a generic control switch, could be an IGBT, a MOSFET or a BJT. Now to control the drive, give the drive for the switch, we need to take a block from here, go to the block library, A block library, and pick PWM single, as it is only one switch that we need to control. And then let us pick one more source block for giving the input to the control element, and that we can take from here, the source. Then we need the labels, we need the power rails. So the generic power symbol, this is for the labels, we'll keep it at one side. We need to label the various parts. We need the ground symbol, of course, it's very, very important. You cannot do a SPICE simulation without the ground symbol. And then we need to include the directive, the include directive. Recall that we would like to include our custom library, which will now start growing. It has two components, diode and the macro diode model. So we will place that there. So these are the components that we would need. So let me first give a label name for that, and then we shall also say that it has to refer to edt01.sub, the same name that we gave for the rectifier, and to that file we will include or add few more custom models. Okay, so let us place. Now this is a DC source, so it should not be a sine. So let us give it a DC source value of, let's say, 12 volts. And this one will be V in. So we have this input source, and this is also a DC source. I will for now keep this at 0.5 volts, and we will call this one as VC, or the control voltage that you would give for the PWM. So let us call that one as VC, which we need to give to the input of the PWM here. So let us organize now for the buck converter. I will like to rotate it and then place it here. and then we need to have a diode. Rotate that, and let us place the diode here. Then we need to have the inductor, place it in line with this so that it's easy for you to draw make the connection wires. Let us rotate the load resistance R0. Place it here. And the PWM, take it somewhere here, and this. Yeah. So these are positions that probably we can make a copy of the ground symbol and paste it so that you have one more ground symbol here. Okay, now next step is to make the connections. So this gets connected here, the emitter to the inductor, diode to the pole, to the capacitance, and here drag it, yes, and then make this connection here, complete this connection, and this has to be connected to this. This will be connected to this, and we have almost all connections. Observe that here it is just overlapping and not making the connection. The spice has not put a node point here, but if it puts a node point, then it is a connection, and be careful, that should not happen. So we shall put a ground node point there, and we will put a ground node here. So I will leave the switching frequency default at 10 kilohertz, which would mean 100 microseconds as ES switching period. Now let us put some nodes here. Now this is my V in node. So I will name it as A. This is our pole node, so name this as P, as we had discussed. This is your output node. We will name this as O. Let us have the gate drive node also, to see how the gate drive looks like. That we will call as G, the gate drive node. And of course you have the control voltage we see here. So if you look at the gate drive node here you will get the pulse width modulated signals, which will be controlling the on-off of this, and how the power gets pumped into the inductor and the output capacitors of the load. Next, let us put in some proper labels. I will say this is switch. There is only one switch. I will not name it as SW1. X means that this is a subcircuit. X PWM means this is a subcircuit. it is named, and D, only one diode, we'll keep maintain that, 1L, so no need to give a number, 1C, and this is our R0. Okay. So I'll give some values. Later on I'll show you how to calculate values. For now, I'll put in the values here. Okay, 10 millihenry, 1000 microfarad, 100 ohms at the output, and 10 kilohertz switching frequency, and you have 0.5 volts as the control voltage here. Now this will complete the schematic part of it. We need to put in the model for this and put in the model for this into the subcircuit. These two are new components. These are subcircuit. The generic model for this will come in there. And how the PWM is made. The PWM is an analog behavioral model, and that also will come in here. ngSpice is very powerful. It also permits analog behavioral model where you can give logic and analog signal processing and interface digital and analog mixed signal processing is also possible. Very, very powerful spice tool for you to have. So let us now go and save here. Good time to save. So this is the buck.ch, which is there in the DC folder here, and I have copied the ADT01.sub from the rectifier example that we did in the last week and placed it here. This contains exactly the same content as that was. Now here we will add two more. One is for the switch and other for the PWM triangle. Now for the switch, I will put in these lines. This is a subcircuit. This is a power switch. The power switch which are there in the schematic. Let me explain in this fashion. Yes. So this is the power switch. When you double click on that, you will see that coming up here in the value field. It has the positive node and the negative node. That's what this is. Positive, N is the negative, and VCP is the control pin. Now it uses a switch and two diodes to model this particular power switch. How it looks like is as follows. Let me open up my writing pad. It goes like this. So I have a switch. This is the switch, and let us have a docking diode like this and a freewheeling body diode in this manner. So this we are calling it as NSP. This is called as NSN, and then there is a control pin NECP. So this is the blocking diode. It allows only the forward path as far as this switch is concerned, and any freewheeling action goes through the body diode, which is D body. So this is essentially what goes in to make up this subcircuit. So let me close this and come back to this. Now here if you see, there is a diode model. The diode model already we have defined for the rectifier. We don't need to define again. There is a switch model which we need to define. This is using the dot model command of SPICE. So switch is also recognized by SPICE, but let us indicate it here. So it goes in at this point. So now we have the switch model and the subcircuit for the power, and we have the power switch well defined. Let us save this. Next, we have to define the PWM. For the case of the PWM block, we shall do it this way. Let me put in the text for the model. So you see here, this is a subcircuit PWM triangle, NP in and NP out, and there is a parameter which is switching frequency, which you can change for different circuits. It has these parts. I have used A as a prefix for these lines here to indicate that they are analog behavioral modeling. Not necessary that you should use A, but it is a good practice. Now it has three major parts, which I will show by going to the notepad. So normally what is done is there will be a comparator, and to the comparator arms, let's say you have plus and minus, you will give a triangle generator here, and this is where the comparison input or the control voltage is coming, and this will get compared with the triangle. So if I am having a triangle which is from -1 to +1 with 0 in between, and let us say my control voltage VC cuts in like this. So you could in effect have your pulse width modulation, which goes like this. And so on. So it will compare with this control voltage, and if the triangle is greater than the control voltage, you will get a high pulse. If the triangle is lower than the control voltage, you will get a low pulse. This is one way. Or if the control voltage is higher than the triangle, you could get the inverted wave shape like this. And whenever the control voltage is higher than the triangle, it will come in like this. So whether it is this or this output would depend upon your plus and minus that you set for the comparator. But you can generate at will the suitable type of PWM pulses with this kind of a configuration. This is effectively what that we are doing here. So we have a triangle generator, just like what we have shown here. We have a comparator, a compare, and then a limiter. What happens is at the output of this will swing to plus 15 and minus 15 to the positive and the negative rate. So you will get a swing which goes from minus 15 to plus 15. We need to limit it to such that it goes 0 to 1. 0 to 1. So normally we will put a limiter here, and this limiter will see that the output will be from 0 to 1. So this is exactly what we have been doing. So we have a triangle generator, a compare and its model, and a limiter, the output of which you see that the lower limit is 0, upper limit is set at 1. This analog behavior modeling is interesting. You should look into the ngSpice manual. It is very elaborate and discuss in detail how to do analog behavioral modeling. So if you go into the ngSpice user manual, and in the chapter Mixed Mode and Behavioral Modeling with XSpice. XSpice is integrated into ngSpice. You will see the analog behavioral models given for various function blocks, and we have used the limiter, we have used summer, these two blocks, and then a triangle generator. Yeah. So if you go into the analog behavioral model, the complete description of each of these models are given and how to use them into your subcircuit, and see that here it is prefixed with A. So try to go through this part of the manual for you to get much better insight into analog behavioral modeling. So coming back to our edt01.sub, let us save and close this. So this is included here. Next step that we have to do is have a buck.cir so that we can simulate that one. We shall now open Notepad and then save it as buck.cir in DCDC. Save. So you would have got that, and let us enter the CIR statements. So let us write buck converter circuit, leave one more space, dot tran, let's say 1 microsecond, 100 milliseconds, use initial conditions, then dot include buck.net, then save this file. So now we have all the things in place: buck.cir, buck.sch, and we have to generate the netlist and then simulate. So let us do that. We go into a terminal, open the terminal, cd to DCDC, we have everything there. So we use the command gnetlist /g spice.spice-stb and output buck.net from buck.sch. So after we do that, the buck.net is generated. You can have a look at that. You will see that these models which we had put gets utilized, and then the netlist comes in here. This is what we had written in the GShem. So now time to simulate. So bring up ngSpice buck.cir. That is loaded. Run the simulation. So the simulation runs. Now everything is available and you can plot. So plot, let us say V0. So this is the plot of the output. It goes and settles at around between 8 and 9 volts, and then we have given a duty cycle of 0.75. How did we give a duty cycle of 0.75? Recall that in the schematic we have given 0.5 volts here, and we know that, let me go to the notepad, we know that we have the triangle which goes from -0, 1.0 to plus 1.0. We have given a threshold, control voltage threshold at 0.5 volts. So this would be 75% of the time, and therefore you will have something like this. So this will have a D of 0.75. So this is how 75% duty cycle would have come. So 0.7, we have given an input voltage of 12 volts. So V naught will be equal to V in into D, which is 12 into 0.75. So this will be around 9 volts. Because of the drops in the switch, these are not ideal switches, and drops in the diode, you will get slightly less than 9 volts. So that is why in the plot you saw it hovering at around between 8 and 9 volts. We could also have a look at the current plot IL. You can see here what to plot. You have the moment anything hash branch is there, means there are current signals available for you to see, and these are the node voltages. This is the current signal. These are all the transients, and steady state occurs somewhere here. You can just take few cycles. So you see the inductor current rising during the on time, magnetically it is getting charged, and the inductor current is falling during the off time. This is when it is getting discharged and gets pumped to the output. So the simulation works, and you can see the various waveforms to understand the buck converter circuit. We shall now go back to our notepad and study a bit more on the waveforms of the primary converter circuits. Quit that. You should play around with these because we have just put arbitrary values. You can improve the dynamics by reducing the capacitance value, and also play around with the L value to adjust the ripple current value, and then save it. Then you can try what happens. So go back to this one. You use the up arrow to get back to that command line, generate the netlist again, then go into ngSpice, run, plot. So let's say you want to see the current. So you see the current dynamics have improved. It has reached steady state earlier than in the earlier case when the capacitance was 1000 microfarads. So in this way you can try to learn a bit more about your circuit by changing the parameters and learning about the currents and the voltages at the various critical nodes and branches. Then you close it, quit, ngSpice, and that completes the simulation. In the case of boost and buck boost converter, what you have to do is change the position of the switches, diode, and the inductor according to their respective topologies, and redo the netlist and then run the simulation. I will leave it to you for trying out the boost and the buck boost converter along same lines as we did for the buck converter.